8.7 Check your understanding. How high above the bottom of its arc is the particle in the simple pendulum above when its speed is 0.81 meter per second? We are neglecting non-conservative forces, so we write the energy conservation formula relating the particle at the highest point, which is the initial, and the lowest point in the swing final as K initial plus U initial is equal to K final plus U final. Since the particle is released from rest, the initial kinetic energy is zero at the lowest point. We define the gravitational potential energy to be zero. Therefore, our conservation of energy formula reduces to. So through this formula, we will find the height of the above the bottom of its arc. So we will divide both side by mg. So, nabilin sa left side is h. Sa right side is equal to 1/2 v square over g. So, kaya na-eliminate man ang m. So, m divided by m, 1. So, eliminate, cancel m. So, v squared over g na lang nabilin. And after that, kaning 1/2, ang denominator i-times na to sa left side while ang numerator i-times na to sa right side. So, ang nahitabo, ang left side nahimog 2h and the right side is nahimo og v square over g. Therefore, through the nga formula, through to this formula, makuha na to ang height nga atong gipangita. So, 2h equals v square over g. Therefore, substitute na to ang given numbers, which is ang v is equal to 0.81 meter per second and g is 9.8 meter per second square. So 2h equals open parenthesis 0.81 meter per second close parenthesis squared over 9.8 meter per second squared. So ang square sa 0.81 meter per second is equal to 0.6561 meter squared per second squared over 9.8 meter per second squared. So, after that, we will divide the right side and it will come up to 0.0669 meter. Then, to get the height, we will divide both sides the constant 2 to eliminate the constant into the variable to get the answer. So therefore, the height is equal to 0.033 meter. Example 8.8 Air resistance in a falling object. So, a helicopter is hovering at an altitude of 1 kilometer when a panel from its underside breaks loose and plummets to the ground. The mass of the panel is 15 kilogram and it hits the ground with a speed of 45 meter per second. How much mechanical energy was dissipated by air resistance during the panel's descent? So, there are only one body is being investigated here. Gravitational force as well as air resistance is acting on the panel as stated in the problem. While gravity is a conservative force, the non-conservative force of air resistance has a negative effect. Work on the falling panel so that we can apply mechanical energy conservation as expressed by. To calculate the energy dissipated, use equation 8.12. The magnitude of the work is represented by this energy. At y initial equals 1 kilometer, the initial kinetic energy is 0. At this point, we set the gravitational potential energy to 0. The non-conservative work is set equal to the energies required to solve for the work lost due to air resistance. So, the solution. The mechanical energy lost due to air resistance is the algebraic sum of the kinetic energy gain and loss in terms of potential energy. As a result, the calculation of this energy is. Therefore, the majority of the panel's initial mechanical energy is equal to 147 kilojoules was lost due to air resistance. Take note that we were capable of calculating energy dissipation without knowing the force of air resistance, only that it existed dissipative. Example 9.1. The Arizona Meteor Crater. Approximately 50,000 years ago, a large radius of 25-meter iron-nickel meteorite collided with Earth at an estimated speed of 1.28 times 10 to the power of 4 meter per second in what is now the northern Arizona desert in the United States. The impact produced a crater that is still visible today. Shows in figure 9.7, it is approximately 1,200 meter or 3/4 of a mile in diameter, 170 meter deep, and has a rim that rises 45 meter above the surrounding desert plain. Iron nickel meteorites typically have a density of 7,970 kg per meter cube. Use impulse considerations to estimate the average force and the maximum force that the meteor applied to Earth during the impact. So, figure 9.7, the Arizona Meteor Crater in Flagstaff, Arizona, often referred to as the Barringer Crater after the person who first suggested its origin and whose family owns the land. So, it is simpler to reverse the question and calculate the force that Earth exerted on the meteor in order to stop it. As a result, we will calculate the force on the meteor and then use Newton's third law to argue that the force is positive. So, in chapter 9, collisions and linear momentum, the magnitude and direction of the meteor on Earth were equal. Using the meteor data provided and making educated guesses about the meteor's shape and impact. To begin, we will use equation 9.6 to calculate the impulse. We then employ the force impulses relationship. To calculate the average force during impact, use equation 9.5. Follow that we select a reasonable force function for the calculate the average value of the function equation 9.4 and set the resulting expression equal to in relation to the calculated average force. This allows us to calculate the maximum force. So, define upward to be the positive y direction. For simplicity, assume the meteor is traveling vertically downward prior to impact. In that case, its initial velocity is equal to negative initial velocity, and the force Earth exerts on the meteor points upward. So the situation at t is equal to 0 is depicted below. The average force during the impact is related to the impulse by from equation 9.6. So we have the mass is equal to the product of the meteor's density and its volume. If we guess that the meteor was roughly spherical, we have thus we obtain. The problem says the velocity at impact was negative 1.28 times 10 to the power of 4 meter per second. The final velocity is 0. Also, we guess that the primary impact lasted about time max equals 2 seconds. Substituting these values gives. This is the average force applied during the collision. Notice that this force vector points in the same direction as the change of velocity vector. Next, we calculate the maximum force. The impulse is related to the force function by. We need to make a reasonable choice for the force as a function of time. We define t equals 0 to be moment the meteor first touches the ground. Then we assume the force is as a maximum at impact and rapidly drops to 0. A function that does this is the parameter represents how rapidly the force decreases to 0. The average force is where delta t is equal to t max minus 0 second. Since we already have a numeric value for constant force, we can use the result of the integral of the obtained max force. Choosing this is a common choice, as you will see in later chapters, and guessing that T max is equal to 2 seconds. This integral evaluates to. Thus, the maximum force has a magnitude of 7.27 times 10 to the 12 power Newton. The complete force function, including the direction, is. This is the force Earth applied to the meteor by Newton's third law, the force the meteor applied to Earth, which is the answer to the original question. Therefore, the function graph contains critical information, so let us plot the magnitude of this function and the average force combined. As for the plot of f of t, recall from calculus that the area under the plot of a function is numerically equal to the integral of that function over the specified integral. So here, that is integral 0 to time max f of t dt equals j. The area beneath each plot has been filled in. The area is a rectangle for the plot of the constant force. Rectangle corresponding to constant force T equals J. As a result, the areas are equal, and both represent the impulse applied to Earth by the meteor during the 2-second collision. The average force on Earth appears to be innermost, and it is regardless Earth. It went unnoticed. The Earth's acceleration was just, which is completely unmeasurable. Nonetheless, the impact produced seismic waves that can now be detected by modern monitoring technology. Example 9.3. Figure 9.11. The fictional starship Enterprise from the Star Trek Adventures operated on so-called impulse engines that combine matter with antimatter to produce energy. Mr. Solo, take us out ahead 1/4 impulse. With this command, Captain Kirk of the Starship Enterprise on the figure 9.11 has his ship the start from rest to final speed of 1/4 times 3.0 times 10 to the 8th power meter per second. Assuming this maneuver is completed in 60 seconds, what average force did the impulse engines apply to the ship? So, we are asked for a force. We know that initial and final speeds, and hence the change in speed, and we know the time interval over which this all happened. In particular, we know the amount of time that the force acted. This suggests using the impulse momentum relation. To use that, though, we need the mass of the Enterprise. An internal search gives a best estimate of the mass of the Enterprise in the 2009 movie as 2 times 10 to the power of 9 kilogram. So, because this problem involves only one direction, the direction of the force applied by the engines, we only need the scalar form of the impulse momentum theorem, equation 9.7, which is, this is an unfathomably powerful force. It goes without saying that such a force would slaughter everyone on board instantly, as well as destroying all of the equipment. Fortunately, the Enterprise is equipped with inertial dampeners. It is left to the reader's imagination to figure out how these work.